this video, we will discuss Euler paths and circuits in graph theory. If we start at a vertex and trace along edges to get to other vertices, we create a walk through the graph. More precisely, a walk in a graph is a sequence of vertices such that every vertex is adjacent to the vertices before and after it in the sequence. If the walk travels along every edge exactly once, then the walk is called an Euler path, or technically an Euler walk. If in addition, the starting and ending vertices are the same, so you trace along every edge exactly once and end up where you started, then the walk is called an Euler circuit, or an Euler tour. Of course, if a graph is not connected, there is no hope of finding such a path or circuit. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. For the next several videos, assume the graphs discussed are connected. The bridges of Königsberg problem is really a question about the existence of Euler paths. There will be a route that crosses every bridge exactly once if and only if the graph here has an Euler path. Let's take a look at what that graph looks like. And that island is connected to all the other islands here. Perfect. This graph is small enough that we could actually check every possible walk that doesn't reuse edges, and in doing so, convince ourselves that there is no Euler path, let alone an Euler circuit. On small graphs, which do have an Euler path, it is usually not difficult to find one. Our goal is to find a quick way to check whether a graph has an Euler path or circuit, even if the graph is quite large. One way to guarantee that a graph does not have an Euler circuit is to include a spike or a vertex of degree 1. Take a look at this graph. Let's say we have K3 here, and we throw on a spike A. The vertex A has degree 1, and if you try to make an Euler circuit, you see that you'll get stuck at that vertex. It's a dead end. That is, unless you start there, but then there's no way to return because you've already used that edge to cross. So there is no hope in finding an Euler circuit. There is, however, an Euler path. It starts at the vertex A and then it loops around the triangle like so. You'll end up at the vertex of degree 3. You run into a similar problem whenever you have a vertex of any odd degree. If you start at such a vertex, you won't be able to end there after traversing every edge exactly once. After using one edge to leave the starting vertex, you will be left with an even number of edges emanating from the vertex. Half of these could be used for returning to the vertex, the other half for leaving. So you return, then leave. Return, then leave. The only way to use up all the edges is to use the last one by leaving the vertex. On the other hand, if you have a vertex with odd degree that you do not start a path at, then you'll eventually get stuck at that vertex. The path will use pairs of edges incident to the vertex to arrive and leave again. Eventually, all but one of these edges will be used up, leaving only an edge to arrive by and none to leave again. Anyways, thanks everyone, and I'll see you in the next video.